Yeah, thank you very much, Peter, for the introduction, and yeah, thanks for the invitation and giving me the opportunity to talk here. And this talk is topic-wise very much related to the previous talk. So I will talk about modeling and simulation of pH-responsive polyelectrolyte microgels. So we heard something about microgels already earlier. So they are cross-linked polymer networks swollen by solvent, and they can serve as confinement for certain reactions, for example, or as model systems for soft spheres. And many of the microgels are responsive to certain parameters in the environment. The most famous example probably is polynipam, which is sensitive to temperature, and it has a lower critical solution temperature. And so when you increase temperature, you go from a swollen microgel to a collapsed microgel. And how large this collapse actually is depends on the cross-linker concentration in this microgel. And we in Aachen, we were fortunate to have funding for research on microgels for the past 12 years. So going from very simple spherical systems, our groups in Aachen were able to, for example, introduce functional groups to use microgels for catalysis or as scavengers for toxin in medical applications, or also to change the architecture from simple spheres to, for example, core shell structures, hollow structures, Janus particles, or even anisotropic shapes. And also, microgels can contain charged groups. That's what I'm mainly interested in. And so the charged microgels show stronger swelling, and depending on which monomer units you use, you can also introduce some pH sensitivity in these microgels. And could also, by electrostatic interactions, have some uptake of other charged guest molecules. And simulation-wise, our group dealing with microgels were looking at these polyelectrolyte and polyampholyte microgels in dependence of pH of the system. And we also looked at some uncharged system, more crowded systems, and crystallization, and also charged microgels in a denser system. But I will not talk about the lower ones today. I will focus on this topic. But of course, we can discuss later if you are interested in any of the other systems. So if we talk about charged microgels, we need to distinguish between strong polyelectrolyte microgels, which basically under all different pH, they have a permanent fixed charge and fixed pattern of charge along the chain as well. And weak or annealing polyelectrolytes, which actually contain titratable monomer units, and the degree of ionization, so the fraction of monomer units which are charged, depends on the pH. So and also the position of the charges along the chain or within the microgel in this topic can change. So as we've seen before, if we plot the degree of ionization against the pH, we get this ideal curve from the Henderson-Hasselbalch equation, which basically would be a monomer unit at infinite dilution, or the first monomer unit to be ionized. And if you connect several monomer units to a chain, the more the chain is charged, the more difficult it gets to ionize the next monomer. So we actually see shift of the pK value, which is like where half of the monomer units are charged, for acids to a higher pH, or if you look at one certain pH, you see a strong decrease in the ionization. So basically, if we want to do a simulation, we just don't only need to take into account the pH with respect to the pKa value, but also the electrostatic potential at the point where we want to deprotonate or protonate the respective monomer unit, which depends on a lot of things like the ionic strength of the system, charge density, microgel swelling, and so on. So we thought we need to get the protonation, deprotonation, and the ionization of the system as an outcome of the simulation rather than an input parameter. So we do Monte Carlo simulations with a certain Monte Carlo step for the reaction. So we use the constant pH Monte Carlo simulation where we introduce a new charge on the chain and simultaneously charge a counter ion. And actually, we include this in the acceptance criterion of the Monte Carlo simulations, and we put in the pK value of the monomer unit and the pH, and we, as a result, we obtain the degree of ionization of the system, both on average and also locally within the microgel. We see later that this differs. And also the network swelling is an outcome, and distribution of counter ions and gas molecules. So if we go to the model, we use bead spring polymer with tetrafunctional crosslinkers, and we use a primitive model for electrolytes. So we use explicit counter ions, which is important for these systems. And the solvent is a dielectric continuum. And yeah, so we have the Coulomb potential. In some cases, we also added attractive potentials, but I will not talk about this today. And as a result, as I said, we obtain the degree of ionization alpha and the swelling and distribution of counter ions. So some years ago, we started with a simplest system, quite idealized network with titratable monomer units, only acidic ones, so polyelectrolyte network. Later on, we moved to alternating polyampholytes, so containing acidic and basic monomer units in an alternating fashion. Moved to core shell polyampholyte networks. And then the most recent results were including gas molecules of opposite charge. So I will talk about only some of these results. So the first one is about the polyelectrolyte microgel, and plotted here is the degree of ionization again against the pH, and compared to the Henderson-Hasselbalch equation, and we see that so from red to blue, the concentration of microgels is decreased, so the simulation box is larger for the blue one, and what happens is that some of the counter ions leave the microgel, so the effect of the pKa shift increases with decreasing concentration. So maybe that's the main result of this set of simulations. And also, if we look at the swelling, the swelling starts at much higher pH, and if we now look at the local ionization of the microgel, we see. Let me first tell you what you see here. The The dashed lines are the global degree of ionization, so the average over the whole complete microgel, and the different colors are the the different colors are the global degree of ionization, basically. So if we go from the center of mass of the microgel to the outside, you see that at the center of mass, you have a slightly lower ionization than outside. That's also due to the connectivity of the network. Also, Peter has done some simulation of star polymers, so the loose ends are more easily ionized. Here, and also if we look at single chains, we distinguish between the inner chains, which have close to the cross-linkers, have the lowest ionization, and the dangling chains, the free end has the highest ionization. If we now, so the main result, you always see a decrease of ionization compared to the ideal case. If we now go to the polyampholyte case with alternating acidic and basic units, we get a new parameter. We get the delta pK, so actually the difference of the pK values of the acid and the base. And we here distinguish between three cases. So this is the case at low pH, the base is fully charged, and then ionization decreases and actually is very low before even the acid starts to get ionized. So the two polyelectrolytes don't know anything of each other. So basically also the ionization is decreased in both cases. The other extreme case is a strong overlap between the ionization of both species, and you see a strong enhancement of ionization both of the acid and the base compared to the ideal case. And at some intermediate case, you actually get up to the isoelectric point. You get an increase of ionization and a decrease on the other side of the isoelectric point. And the ionization of both species actually, so the net charge is 0, but the ionization of both species actually increases with increasing delta pK. Looking at the local ionization, we also can distinguish between the two cases, and now we look only at the acid, and we see for this, for the case where they don't see each other in an ionized state, we see the same behavior as for the polyelectrolyte, of course, and on the other hand, for the overlapping ionization, we see actually a decreased ionization at the periphery, close to the surface of the microgel. Which I forgot. And for the case in the middle, we have a partial overlap, and we both see up to the isoelectric point, we see a decrease in ionization at the surface and an increase on the other side. Okay, concerning the swelling, if we plot it against the pH, we get like a lot of different curves. And with the collapsed microgel, either uncharged or both species charged at the isoelectric point. Or if we just plot everything against the effective charge of the microgel, we basically see that the swelling mainly depends on the effective charge. So now, how much time do I have left? So, going to the uptake of guest molecules, of course, we found this interesting in itself, but also microgels are investigated as like carriers for certain drugs, and in this case, there's one, an increase of the number of like deaths connected with antibiotic-resistant bacteria, and actually very few to know new antibiotics have come to the market a long time ago, and this problem actually will increase. Or is expected to increase in the coming years. And one species which is quite promising are antimicrobial peptides. And they suffer from like there's toxicity and also stability issues in the body. And Martin Malmsteen's group in Copenhagen, they actually looked into how microgels or polymer gels can be used for delivery of these antimicrobial peptides, and found that the toxicity is reduced and also the stability of the antimicrobial peptides. The sidetrack. So we actually looked at a polyelectrolyte microgel, like from the first part of the study, and added some oligopeptide or some oligomers, charged oligomers, and these ones. So this is a network, negatively charged, and positively charged the oligomers, and basically otherwise it's the same model. We have explicit counterions and Coulomb interactions. So going from low pH and charged oligomers, through intermediate pH with microgels and oligomers charged, we go to a fully charged microgel, but very little charged oligomers. And I just want to show you the variation of two parameters, like the delta pK value, as I talked about before, and the chain length. So these are results from delta pK values. So as not all chains are going into the microgels, I mean, the reason for the oligomers to go into the microgel is release of counterions by associating the oppositely charged macromolecules. And here we need to distinguish between chains which actually stay outside the network and chains which go inside. So the chains outside the network just behave like polyelectrolytes, which I told you before, that the degree of ionization is reduced compared to the Henderson-Hasselbalch equation. And we also look at the network chains and the oligomers inside the network, and there, of course, we see an increase of ionization, which is stronger if you have a larger overlap of the pK values. Also, we looked at the uptake and the network swelling. I will not go into detail for this, but maybe it's interesting that we see an optimal pH for the uptake. And if we look at the chain length, we of course see for the chains outside the network, we see that the effect, the more monomers we connect, the effect, the polyelectrolyte gets stronger. And for the for the network and also the oligomers inside the network, we see a higher increase of the network ionization in the presence of the longer chains, because the counter entropy gain is stronger the longer your chains are, which you replace them with. And also you can see this in the uptake. And the network swellings, there are two effects coming into each other. This now, because I think I run out of time. And so what I want to tell you with this talk, that it's important if you do simulations of pH-sensitive polymers, it's important to take into account the electrostatic interactions of the system and actually obtain the ionization as a result and not as an input parameter in the simulation. And for the weak polyelectrolytes, we in general see a suppression of the ionization, whereas that's, if you mix oppositely or acids and bases, we can see both a suppression and an enhancement depending on the parameters of the system, which are quite difficult to predict just from the beginning. And also, if we have like charged gas molecules, this is an important part. So the main message is this one, and thank you very much for your attention, and let me thank the group and the funding.